Let me try.
I think it will be okay. Huh?
Now, I think there is something. Yes, okay.
Yeah.
Yes, yes.
Okay, so during the first lecture of today, I'm going to explain Bedford-Taylor theory, and then we have a break. And then in the second lecture of today, I'm going to explain the proof of a celebrated uniform a priori estimate for solving complex Monge-Ampère equation. So, but let's start with Bedford-Taylor theory. So the goal of this first lecture of today is to explain the definition and the properties of the Monge-Ampère, which I will denote by this, like this, which will be 1 divided by V, omega plus ddc phi to dn, where so V is the total volume of the manifold with respect to the Kähler form omega, and phi is some omega persomonic function which is bounded. So this complex Monge-Ampère operator here makes sense when the function phi is smooth. And the goal of this first lecture is to explain how to define this operator when the function phi is not smooth anymore, no longer smooth, but rather merely bounded. Okay, so that's the goal. And at first, so let me maybe change slide. The first thing I'm going to explain is how to define this object for continuous functions. The theory is much simpler for continuous functions. So let me start by describing this. So let me recall that in last Tuesday, we have denoted by k omega the set of those functions phi, which are smooth, defined on the compact Kähler manifold X with real values, and so that the quantity omega plus ddc phi is another Kähler form. So dd bar homologous to omega, and it's yet another Kähler form, and this is the so-called set of Kähler potentials. This is a standard terminology for them. And let me recall that PSHX omega, this was described on lecture 2. This is the closure of K omega, closure for the L1 topology. So I recalled a result of Domailly that any omega persomonic function is a decreasing limit of smooth scalar potentials. But of course, an obvious observation is that if phi is not only omega persomonic, but it is continuous, then phi is the uniform limit. There exists phi j Kähler potentials such that phi j uniformly converge towards phi. Okay? And if you like, the theorem, which is both a theorem and a definition, is that if I consider the Monge-Ampère measures, or maybe, I should have started by that. So let me first make a second observation. So observation 2 is that for any psi which is a Kähler potential, so the Monge-Ampère of psi, which is 1 divided by V omega plus ddc psi to the n. So this is a well-defined smooth probability measure, or volume form, if you like. Probability volume form. And this is simply because by Stoke's theorem, if you compute the total mass of this smooth measure, then by integration by part, this is the same as the volume of x with respect to omega, and this is this v that we are divided by in the definition of ma of psi. Okay? So now that this observation has been made, the theorem definition is the following. The measures ma of phi j above weakly converge towards a measure, a probability measure, let me denote it by mu phi, which is independent of the choice of the approximant. And therefore, we set ma of phi, so the complex Monge-Ampère measure of phi, by definition, is this measure mu phi. Okay, so the theorem says two things. First, you pick one approximating sequence phi j, which uniformly converges towards phi. Then the corresponding smooth complex Monge-Ampère measures of phi j's, they weakly converge towards something. And this something is independent of the choice of the approximants. Therefore, it makes sense to define this as the complex Monge-Ampère measure of the function phi. So let me prove that, because actually the proof is rather simple. And the proof actually relies, or is a simple consequence, on the following lemma. Namely, if you pick two scalar potential, U and V, and you pick chi, a smooth test function, then the integral, so you consider Monge-Ampère of U and Monge-Ampère of V like radon measures. So you test them against this test function, and you look at the absolute value of the difference. And then the claim is that this is less or equal than n, the complex dimension, times the L infinity norm of the difference of U minus V, times the C2 norm of the test function. So I'm going to prove this, but as a consequence, let me observe that if you plug this in into the approximating sequence, then you see that phi j minus, say, Monge-Ampère of phi k with, say, well, whatever. Then this is less than n times the C2 norm of chi times the uniform norm of the difference phi j minus phi k. And since this goes to 0, because phi j uniformly converges towards phi, this tells you that the Monge-Ampère of phi j against chi is a Cauchy sequence, if you like, or converge to something. Okay? And similarly, if you take, let me write it like this. If you replace here Monge pair of phi k by Monge pair of psi j, which is another approximating sequence, here you will get phi j minus psi j infinity. And so for the same reason, this will converge to 0. So, okay, so the theorem and the definition is a simple consequence of this lemma. So let me prove now the lemma. Well, this is a simple integration by parts, which relies on the following algebraic observation. So if you look at omega u, what am I doing? Up. Omega u to the n minus omega v to the n. This is ddc of u minus v, wedge the summation of omega u to the j, wedge omega v to the n minus j minus 1, from j varying from 0 to n minus 1. So this is a simple algebraic factorization, if you like, and therefore this tells you that the integral of chi Monge pair of u minus Monge pair of v, let me add absolute value, this is the same as the integral of chi ddc u minus v wedge this summation. Now I integrate by parts using Stoke's theorem, and this is the same as the integral of u minus v ddc of chi wedge this summation, and the summation is a closed form, so the ddc will not affect the will not contribute if you plug into the summation. So this is what you get by Stoke's theorem. And you can now bound from above and from below ddc of chi by the C2 norm of chi times omega. You can bound from above and below u minus v by the L infinity norm of the difference, and you end up with u minus v infinity chi C2. Oh, sorry, something is missing in my formula. This is that in the Monge pair, I divide by v, so there should be a 1 divided by v here. So let me add it here as well. And then what remains is the sum from j going to from 0 to n minus 1, and then the integral of omega u j, omega v, n minus 1 minus j. But now each of this integral, again by Stoke's theorem, this is equal to v. So I get n times v divided by v. So this is n times u minus v infinity chi C2 as desired or claimed in the lemma. Okay, so you see that with this simple integration by parts and by using uniform approximation, it's easy to define the Monge pair measure of a non-smooth but rather continuous omega plus harmonic function. So let me explain on some example what you get that way. So let me take X, which is the complex projective space, omega, which is the Fubini-Studi form. And let me take, for instance, phi of Z, so in homogeneous coordinate, which is the maximum of the logarithm of Z j, or Zi maybe. So I varies between 0 and n. And then to have a well-defined quantity, I should subtract the log of the norm of z, which, as we explained last Tuesday, is the potential for the full Guedj-Keller form. So this is a globally well-defined omega personal function on Pn, which, as you see, or you can check in local charts, affine chart if you like, is continuous. And actually, it's even Lipschitz continuous, if you like. But it's not smooth. Of course, when you take maximum, you are doing things like this, right? So you get Lipschitz, but here it's not smooth. Okay, so what does this definition give in this particular case as a for the Monge-Ampère measure? So the claim is that the Monge-Ampère of phi is, in this particular setting, the Haar measure on the torus S1 to the n, which is here embedded in Pn as you look at the set of those points, Z in Pn, so that Z0 in absolute value is the same as Z1, etc., is the same as Zn. So this guy is a torus S1 to the n embedded into the complex projective space. And my claim is that this complex Monge-Ampère measure of this continuous omega present function is exactly this Haar measure. So how to see that? Let me give two possible approaches. So first, following the definition, you can consider a smooth approximation, and here is a possible way of approximating the function. You look at the phi j's, which are 1 divided by 2j log of z0 to the 2j plus etc. plus zn to the 2j minus log z. And it's perhaps not obvious at first sight, but this is a more or less classical way of approximating the maximum. So you see that when j grows, the powers of the modulus of the coordinates, the one that will be the dominant term is the one that has maximum modulus. So in the very end, what you get is that this behaves, since you renormalize by dividing by 2j, what you end at the end is the log of the maximum of the modulus of the coordinates. So phi j turns out to converge towards your original phi, and you can compute the Monge-Ampère of phi j. So because phi j is smooth, this will look like something like fj times a volume form, say omega to the n, and you have a fj which is completely explicit, and you try to see that it weakly converges towards this measure mu, which is the Haar measure, which is the, or if you prefer, the Lebesgue type measure. Lebesgue measure on S1 to the n. So you can indeed do the computation. I leave that as an exercise. It's not very difficult, but neither extremely pleasant. So here is a more conceptual and perhaps more pleasant approach, which is like this. So first, which is a bunch of observation. So first, you can make an explicit computation of Monge-Ampère of phi and realize that this is 0 where phi is smooth. So you see that, as I explained, or as I briefly draw, when you do a maximum, you are introducing cusp like this. But of course, here, And here, the function, one of the coordinates is really dominating the other, and the function is smooth. And you realize that the Mongeon pair is 0 wherever phi is smooth. And pushing this observation one step further, you can realize that the Mongeon pair of phi is 0 actually outside this torus, because outside this torus, phi only depends on n-1 or on less than n variables. So you should keep in mind that the complex Mongeon pair, it is something I actually perhaps never said. It's in local coordinate for smooth function, you are taking the determinant of the complex Hessian of the matrix, of the local potential. So if the function that you're taking this determinant of depends on strictly less than n variables, then of course the matrix will have rank less than n, and so the determinant will be 0, and so will be the complex Mongeon pair operator. So observing this, you realize that the Mongeon pair has support in this torus. On the other hand, because the potential is invariant under rotation in each coordinate, so is the complex Mongeon pair operator. And finally, the total mass on Pn of this Mongeon pair is 1, because it's, by definition, it's a probability measure, and there is a unique such measure. This is the Haar measure. So in a sense, there is not much choice for the end result of the complex Mongeon pair of this particular function. Okay, so this second approach somehow is more pleasant with some background, because you see that there is no choice. So without much computation, you can realize that this is what the Mongeon pair has to be. But from the point of view of the very definition, I think the first method is perhaps useful, but I leave it as an exercise. Okay, so that was my first example. And now I would like to move on to the heart of Bedford-Taylor theory, which concerns the case of bounded functions. So similarly, we have the following theorem definition. So given phi, which is omega plus harmonic and bounded rather than continuous, if you pick phi j, a sequence of scalar potential with phi j decreasing towards phi. So this is possible thanks to the Maïs results that I recalled in lecture 2. Then the theorem says that Mongeon pair of phi j weakly converges towards some measure, probability measure mu phi, which is independent of the approximating sequence. Hence, we set Mongeon pair of phi, which is equal to mu phi. So the proof, I'm not going to give it. The proof is a bit more involved. Again, it relies on integration by parts, but there is also a twist, which is a notion of gluing technique that I don't want to enter here. But maybe I would like to say two things in order to convey at least some of the ideas. The first is maybe So the heuristic idea behind this, the fact that it works, is that omega plus harmonic functions are quasi-continuous. That is to say, they are continuous on sets x minus g, say epsilon, where g epsilon is an open set of measure less than epsilon for each of the Monge-Ampère measures involved. So in other words, you are very close to being in the previous situation, except that you need to work with a small error term. And this is really what lies behind the fact that you can extend this theory from continuous to bounded. But the problem is that this heuristic idea turns out to be justified at the end of the theory. So you need to develop the theory, prove the theorem that I'm not going to prove here, to eventually realize that this is what is happening. So at least the heuristic idea is that those functions, although omega plus harmonic functions are far from being continuous, they turn out to be almost continuous. And then another point I would like to emphasize is that this is a local theory, although I am presenting it on compact Kähler-Harmony form. This theory has been developed by Bedford and Taylor in pseudo-convex domains of Cn. And in that case, it is the first important step is to establish uniform bonds on Monge-Ampère masses. One advantage of the compact setting, as I already used in the previous slides, is that the total mass, if you normalize things, is constantly equal to 1. I'm dealing with the probability measures. It's not the case in local domains, but it is true that the Monge-Ampère masses are bounded as soon as the functions are under that you are considering are uniformly bounded. And this is the so-called Chern-Levin-Nuremberg inequalities. And these are very important, so I'm at least going to state them. So if U is parasomonic in some domain, so let's say omega is a pseudo-convex domain, bounded pseudo-convex domain, pseudo-convex in Cn, and U is parasomonic in omega and locally bounded, and assume that K is a compact set. You give yourself two compact sets, K and L, with K being contained in the interior of L. Then there exists, then the Monge-Ampère mass of U on the small compact set K is bounded from above by CKL times the n-infinity norm of U on the big compact set L. So in the local setting, you cannot expect that the Monge-Ampère mass is always fixed or bounded from above by 1, but at least if the function is bounded, then you have a uniform bound on the Monge-Ampère that you are considering. So assume, if you like, here that U is smooth, And the clue of this inequality is that you have a uniform bound on the Mogent pair of a smooth prosomanic function just in terms of its L infinity norm. And the proof is very simple, so maybe I should give it. So here is my domain, omega. Here is my smaller compact set, K. And here is my bigger compact L with interior containing K. Then pick chi, a test function, such that, let's say, chi is non-negative and chi is identically 1 near the compact K. Then you see that the integral, that the mass of the Mogent pair of U on K, well, is certainly bounded from above by the total integral in omega of chi ddcu to the n, because ddcu to the n is a positive measure, chi is non-negative, and chi is 1 on K. Okay, so you are just enlarging this mass that you try and control. Now you can integrate by parts, because chi has compact support in omega, it is a test function, and what you get is that this is u times ddc chi, where ddcu to the n minus 1. And you can bound u from above. So here, ddc chi, so I forgot to say that chi is 1 near K, and the support of chi is included into the interior of L. Okay, I can do that because I assume that K is included into the interior of L. So in doing so, you see that chi only contributes not on omega, but rather on the interior of L. So I can bound from above by the infinity norm of U on L times the C2 norm of chi, and the C2 norm of chi is some contribution of the geometry of the way K sits into L, and times the integral on, let me call K2 the support of chi, and then what? And then it remains beta, which is the Euclidean volume form, times ddcu to the n minus 1. So with this integration by parts, I see, oh, sorry, I realized that, blah, blah, blah. It's not u to the, I forgot the power. So it's in this proposition of Chan-Levin-Nuremberg, by homogeneity, it's clear that this is what you should get. The Mogent pair is bounded from above by the nth power of the n infinity norm of u. Okay, so sorry about that. And I've done one integration by part, and you see that there is 1 power of the n infinity norm of u that shows up. And then you go on by induction, doing n integration by part, and you will get C prime or Cn KL, U infinity to the n times, in the end, you will get the volume of L, say, the Euclidean volume of L. Okay, so that's for the proof of the Chan-Levin-Nuremberg inequality. And let me make one remark here. This is that actually, I don't really need to control the n infinity norm of U on the whole of L. As you see from the proof, what was really crucial here, in passing from here to here, is the n infinity norm of U on the support of ddc of chi. And because chi is identically 1 on the compact set or near the compact set K, actually I can replace here the n infinity norm on L by the n infinity norm on L minus K. This is actually really what matters and what shows up in the proof. Same thing here. And therefore, what it tells me is that the same holds if U is not locally bounded in omega, but has, say, to simplify, isolated singularities. So you see in my omega here, if U is, for instance, prosomonic in omega, so this is omega, and U is locally bounded in omega minus, say, one point, which is this point A here. Then I do exactly the same proof, putting A inside my compact set K, and I get uniform bonds on the Monge-Ampère mass. And the consequence of that is the following theorem definition, which I guess is due to de Mailly in the late 80s, which is an extension of Bedford-Taylor theory to the setting of, say, prosomonic function which are with isolated singularities, say. And I'm not going to write it precisely, but the same theorem holds, namely, in my theorem definition here, if you replace L infinity of x by L infinity of x minus finitely many points, for instance, then you pick smooth decreasing sequence of scalar potential, then again, the Monge-Ampère measures will converge toward a unique measure which is independent of the approximate. And a consequence of that is what I have used in lecture 2, the Monge-Ampère measure of Green's functions, is well defined. So let me maybe give an explicit computation in a particular setting. Let's see. Well, before that, so I'm going to do that in a minute, but before that, let me also add, let me see. That was the proof. That was for bounded. Okay, so let me add as a final spot in this part 2 that one can more generally consider mixed Monge-Ampère measures. So if phi 1, phi n are omega prosomonic and bounded, or possibly locally bounded outside finitely many points, then one can make sense of omega plus ddc phi 1, wedge omega plus ddc phi n. And maybe let me divide by the volume so that this is a well-defined probability measure. With good continuity property. But when am I going to say this? Yeah. Such that, so maybe let me add as a theorem. So, well, so remark, if you pick numbers tj's in between 0 and 1, then as I briefly explained in lecture 2, sum of tj phi j is omega prosumonic and bonded. So you can consider the Mongeon pair of this guy. And what you will get is that this is 1 divided by V times the sum of from J equals 1 to n of Tj omega phi j to the n. And then you can develop by the binomial expansion, and what will show up is this kind of measures here. So this remark is perhaps too abrupt, but it is to say that somehow the definition of the mixed Mongeon pair measures from an algebraic point of view is already contained in the Mongeon pair measure of a one single function once you understand that you are dealing with a convex guy, convex set. And let me finish this part with the following fundamental theorem, which is a mild extension of the definition, is that whenever phi j is omega prosumonic and bonded, and phi j decreases pointwise to phi, which is also omega prosumonic and bonded, so it is a pointwise convergence, then the Mongeon pair of phi j weakly converge towards the Mongeon pair of phi. And so the Mongeon pair of phi is defined that way, but taking phi j as scalar potentials and realizing that the limiting measure is independent of the choice of approximates. But now the little extra claim is that if you now take any bonded decreasing sequence, so their Mongeon pair will again converge towards the limiting measure. And let me maybe warn you that this operator, phi goes to Mongeon pair of phi, is not continuous for the L1 topology. So I will give an example in a few minutes. So it is continuous for this particular way of approximating, so for decreasing sequences. Okay, so let me move on to describing a few examples. And maybe first, so I should perhaps, to be honest, say that in general, nobody knows how to compute explicitly complex Mongeon pair measures. This is a very highly nonlinear operator, so it's very difficult to compute explicitly unless you have lots of symmetries. So let me use here, describe examples where you have lots of symmetries, namely radial examples. And let me start with the somehow simplest one, perhaps. So you take the logarithm of the norm of C, which is prosumonic in Cn, and locally bounded, except at the origin. And then the claim is that the Mongeon pair of this guy is the Dirac mass at the origin. And let me, because I skipped this computation for the previous example, actually do the computation with the following approximation. So I'm considering 1/2 of log of the norm square of z plus epsilon square. These are smooth prosumonic functions decreasing towards L pointwise as epsilon zero, as epsilon decreases to 0. So you can compute the Hessian of this smooth approximation. So let me put the 2 here maybe. And what you get is what is z beta divided by z square plus epsilon square. And when I differentiate twice, I get this. So delta alpha beta divided by z square plus epsilon square. So this is if I differentiate the numerator, and then if I differentiate the denominator, I get minus z alpha bar z beta divided by z square plus epsilon square square. Okay, so when I take the determinant, I will get 2 to the n, determinant of this complex Hessian, which is what? Either, so by n linearity, either I always take the first term, and then you see I have identity divided by 1 divided by z square plus epsilon square to the n. Or I take one of the term on the right, but this matrix here has rank 1. So I can only take it once. So what I do get is minus the sum from alpha going from 1 to n. And each time the only contribution will come from the diagonal. So I get z alpha square divided by z square plus epsilon square to the power n minus 1 coming from here and 2 coming from here. So in the end, I get n plus 1. And this mod out and gives me epsilon square divided by z square plus epsilon square to the n plus 1. So as epsilon goes to 0, you see that ddcl to the n is indeed 0 in Cn minus the origin. And on the other hand, the limiting measure is non-negative. So ddcl to the n is some C, say, some positive constant times the Dirac mass at the origin. And you can compute this positive constant simply by passing to the limit and rescaling in here, or by a global argument telling that there is no choice, but C has to be equal to 1 for global reason, because the growth at infinity is exactly logarithmic. And well, there are plenty of ways to see that. But in any case, you see that you have part of the explanation of the properties that I was needing last Tuesday when proving Skoda's theorem. Okay, so time is running. So let me, I wanted to discuss another example, but actually I'm going to skip that. Let me just say that if phi, maybe let me use the notation u of z, is log plus of z, meaning this is the maximum of log of z and 0, then I leave as an exercise to show that the Mongeon pair of the DCU to the n is actually exactly the normalized Lebesgue measure on the sphere, on the unit sphere S to n minus 1. And this can be done again in two ways, either by approximation or by slightly more conceptual arguments. Okay, so I want to skip this. So I'm going to run out of time. What should I skip? Okay. Let me maybe briefly mention two things. Okay, yeah. I promised an example of discontinuity. So maybe this is one. Let me consider uj of z, which is 1 divided by 2j log of 1 plus z1j plus z2j square. So clearly, I leave you as an exercise, but it's a simple one to check that this converges as j goes to plus infinity to u of z, which is the maximum of log z1, log z2, and 0, with Monge-Ampère of u, so ddc u square is, as we already explained, the Lebesgue measure, the normalized Lebesgue measure on S1 cross S1. So Z1 equals Z2 equals 1, while the Monge-Ampère of Uj is identically 0. So you see that you have here the convergence is in L1, and you see that you have Uj converging to U, but the Monge-Ampère do not converge one to another. So Monge-Ampère is discontinuous for the L1 topology. Next week, I will discuss a spatial topology in a spatial context, which is somehow interpolating between uniform convergence, which was good, and L1, which is not enough. Okay, but remark that phi goes to Monge-Ampère of phi is continuous for monotonic sequences. And this was almost by definition. This was the theorem definition. And this is an important theorem from Bedford and Taylor in 82. So if you have an increasing sequence of locally bounded Poisson-like functions, then the Monge-Ampère measures do converge towards the Monge-Ampère of the limit. And this is a slightly more complicated theorem than the one that I mentioned without giving the full detailed proof. Okay, now I would like to skip many things I was planning to say and jump to a preparation for the next lecture. So I will need a tool that I already mentioned, but before that, so maybe that's my part 4, I'm not sure. And I need to at least mention the important Dirichlet problem that goes back to Bedford and Taylor in 76. So that's the first foundational paper by Bedford and Taylor. So if how should I phrase this? Let me U assume U is pro-harmonic and bounded in a neighborhood of the unit ball or a ball in Cn. Okay? Then there exists a unique capital U, which is pro-harmonic in B and bounded in B, such that U coincide with little u at the boundary of the ball, and the Monge-Ampère of capital U is identically 0 in the ball. So you have seen examples, very special examples that I mentioned of Monge-Ampère of periharmonic functions, bounded ones, with Monge-Ampère being 0. And there are actually very many of them, and this theorem is a way to construct a lot of them. And the proof goes by approximation. So the proof requires quite some work, but it's one you treat. It goes in 2 steps. Yeah. One, you treat the case where U is actually smooth. And by smooth, it suffices actually to treat the case where U is C2 smooth or even C11 smooth. And then one realizes that U is also C11 smooth. Let me, to be precise, say it's C11 bar smooth, but I don't want to explain this right away. And U, the solution is actually constructed by a Perron method, is the supremum of functions V, which are periharmonic in the ball, and which lies below U. Okay, and then you proceed by approximation. And you pass to the limit, smooth decreasing uj, plus pass to the limit using the continuity of the Monge-Ampère. So as I said, Monge-Ampère is not continuous in full generality, but it is continuous along monotonic sequences, which is what you can do here because you approximate by monotonicity. Okay, so the Dirichlet problem is a much more general type of problem, but this is the one I'm going to need. So I'm going to use the fact that I can locally solve Monge-Ampère equals 0 with given bounded boundary data. And here is the reason why. And this is the tool I will need in the next lecture. So let me mention that again. So given the corollary, if you like, is that given phi, which is, so I go back to the compact setting, it is omega periharmonic and bounded on X, and fix be a small ball in X, meaning you pick a point in X, you use local coordinates, and you take the image of a ball of small radius through these local coordinates. Then there exists maybe a ball, let me denote it by BR, and R will be the small radius. There is a unique phi R, which is omega periharmonic and bounded on X, such that, well, phi R is actually identically equal to phi outside of the ball. And in the ball, the Monge-Ampère, so the compact version of the Monge-Ampère of phi R is equal identically to 0 in this small ball. And moreover, phi r is actually bigger than phi, and phi r decreases to phi as r, the radius, decreases to 0. So in order to prove this corollary, you apply the previous Dirichlet local problem using local charts, and you glue together the local data, this capital U that we had, with the global phi. And it is a fact that I didn't have time to explain that there is a so-called maximum type principle, which says that you can indeed do that. So you can indeed glue, because the solution of your Dirichlet problem, so let me come back to the Dirichlet problem, the capital U that you construct that way with this theorem is indeed bigger than U. And because it matches U at the boundary, if you have a U which is well defined outside of B, you can extend capital U as saying it is equal to small u outside of B, and you gain another parametric function which is a bit above U in this ball, okay, and satisfies this Monge-Ampère being 0 in that ball. Okay, and a consequence of that, a simple consequence of that, once you know this corollary, you obtain the following proposition, which I mentioned in lecture 2 and which I'm going to use in lecture 4 after the break. If H is fixed, maybe let's say it's infinity smooth to simplify, and you set P of H, which is the supremum of those functions U, which are prosomonic, and U lies below H. Then P of H is omega prosomonic and bounded, and the Monge-Ampère of this envelope is supported in the contact set C, like contact, of those point X, such that the envelope is less than H at point X. Sorry, is equal. And the reason is that at points if you are, say, this is X, and maybe there is a piece here where the two coincide, but let's pretend you have a point here, X, outside of the contact set. So this is C, say, and this is outside of the contact set. Then you pick a small ball here, and you replace P of H by the solution of by using the corollary. So using the solution of the Dirichlet problem in this small ball and gluing things together, then you will get another function. So you replace P of H by this, I don't know, capital phi r using the corollary above. And this function phi r, because it decreases to P of H as r goes to 0, and because P of H is strictly smaller than H where you are working, then phi of r will be less than H if r is small enough. But then phi of r is equal to P of H, so it's also less than H on the contact set. So it means that phi of r is a prosomonic function which lies below H, hence, actually phi of r is less than P of H. But by what I said from the corollary, it has to be actually equal to P of H, so the Monge-Ampère of P of H is equal to the Monge-Ampère of phi r is equal to 0 in this small ball. And this is true for any point outside of the contact set, so what you get at the end is that the Monge-Ampère of the envelope, this is called an envelope, is indeed supported on the contact set. Okay, so I perfectly understand this was a bit abrupt, but that's I'm running a bit out of time. This technique here is very standard in studying many PD problems. It is called balayage. And I'm going to, in the next lecture, describe how to or describe part of the proof of Yao's celebrated theorem that you can solve Monge-Ampère equals a smooth volume form. So describe the scheme and explain the main lines of the proof of an important L infinity a priori estimate. And in that proof, I will use this quasi-prosominic envelope. This is why I wanted to finish by it before the break. Okay, so you're probably tired. I've been speaking for more than an hour. So I suggest we stop now. Maybe if you have some quick questions before the break, or we can save them for later. Let me know.